you can only estimate the kind of slow modes accurately from the data. The ones that are sort of faster fluctuating, you don't get them exactly. So the equation mathematically is exactly invertible. If you put in the true covariance matrices, it gives you the true A matrix. But once you put in finite sample errors, then only the slow modes can be recovered, which can be expressed as the inverse, which gives you the, which is dominated by the slow modes. And just to conclude, I'll skip the, I'll just say that I've started trying this on the real data. Some of the results that come out match what is known about biology. You also get nice sparse networks. So it seems that with this approach, at least something interesting at the beginning of a nice model might be coming out. So just to summarize, I've shown you how, if you use these branching processes, you can derive fluctuation dissipation relations that don't involve any time delay, but just same time measurements in the kind of, at the tips of a tree. It's possible to reconstruct the causal links, at least for the moment, if the dynamics is reversible. And what is needed now is just a lot of extensions of the model. For instance, the model where you assume that all cells divide exactly at the same time is completely not realistic. You want the cell division time to be, again, some stochastic variable, maybe with some exponential rate. So that's something to work on. And then what I didn't discuss at all, but what I'm really interested in is the question of spatial correlations. So there's an interesting phenomenon that when cells divide, their daughter cells actually stay in close proximity. And that means the trees that I discussed, I just presented them as kind of time trees, but they're actually, in the real system, space-time trees. And so it would be interesting, and this is a figure to conclude. So what I'm hoping to achieve is, this is what you do in physics. You generate time series data, have your fluctuation dissipation relations. This we cannot do in biology. Instead, we can get some of this information about proliferation, where it is possible to do experiments. But if we can now extend it to spatial correlations, based on this fact that when cells divide, they kind of stay close to each other, that would be enormously helpful, because as was mentioned already, these days measuring spatial data has become very easy. So that's kind of where I'm hoping to go next. Sorry if I went a bit over time.
Okay, thank you. Questions?
I'm just a little bit confused because I was expecting, I'm not an expert in the field, but the gene network to be highly nonlinear. Mm-hmm. So the fact that then you're trying to do with the linear approach, so do you really able to capture something, or there is, right?
So, I mean, linearity is obviously approximation. I mean, even just that we're assuming that the states are normally distributed, that's also a big approximation. We know it needs to be more kind of Poisson distributed. But it seems, at least when you apply it to the real data, you do recover some things that are known. Of course, if you compare it with like a real perturbation experiment, say the real experiment predicts there are 40 targets, maybe you predict the strongest 5 to 6 maybe correctly. So it's obviously a limitation. Yeah.
Tom, I had a clarification. So you said that the correlations, right?
Mm-hmm.
They come from 2 different branches, right?
Mm-hmm.
But then I think you explained it where.
Like this is even without any tree structure. So this is just two random walkers that start from an initial state. And so if you apply to the tree structure, every 2 endpoints are independent given the state of their most recent common ancestor.
During the session. Let's thank all the speakers. Make sure that everything runs on time. So let's thank them. The electrical team, which is also part of the same thing, so let's thank them as well. I think in a really very short time span. So we are really grateful to this person. So we'll thank. And finally, this program could not have been possible